Hi, welcome to Adaquity. This video is in continuation with the previous video where we saw how traveling salesman problem can be applied in real life. If you haven't watched it yet, the link is provided in the description box below or in the iTab above.
Hey, have you been? Long time no see.
Hi, I'm good. What about you?
All's well. So, where are you traveling?
I have to travel to different cities on a single trip. I was wondering which route should I take that would minimize my traveling costs.
Oh, that's pretty easy. You can simply use the traveling salesman problem. That would definitely help you in minimizing your traveling costs.
Wow, that seems interesting. But how does this work?
Well, there's whole mathematics behind it. Would you like to know?
Yeah, absolutely. I would love to know about it.
So, let's consider a situation.
A manufacturing company situated in Surat has to send its goods to the warehouses situated in three different cities, viz. Mumbai, Jaipur and Indore in a single trip. The company aims to minimize the total transportation cost. What route the company should opt to have the minimum transportation cost? This is the matrix representation of a problem. This has already been explained in detail in our last video. Here, 1 unit is equal to 1000 rupees. The city Surat is denoted by letter A, Mumbai by B, Jaipur by C and Indore by the letter D. Now you must be wondering why infinity is used whenever the person is traveling to the same city itself. Ideally, we should be taking 0 in place of infinity when a person travels from the same city to itself, but if you think carefully, then you can understand the reason behind taking infinity. For example, let us consider taking 0 instead of infinity. This way, the aim of our problem will not be fulfilled because a person ends up considering these zeros as well during the assignment process. He will be traveling to the same city again and again and he won't be able to change the city. So in order to avoid such a situation, we use a huge value like infinity, or we can use a dash also. Now coming back to a problem, we'll use the Hungarian method to solve the problem, and it becomes very important to know about the Hungarian method. So if you have missed that out or you want to get an idea about it, you can watch our video on the Hungarian method and the link for the same is provided in the description box below or on the iTab above. According to the Hungarian method, the first step is row reduction. As you can see, the smallest elements in the first, second and third and fourth row are 6, 5, 7 and 4 respectively. So subtracting each of these from all the other elements of their respective rows gives us this as the resultant matrix. Second step is column reduction, applying the same operation with the smallest elements, that is 1, 0, 5 and 0 respectively. In each of these columns, we get this as a resultant matrix. Step 3 is assigning zeros, which has row scanning first. Since there are 2 zeros in the first row, skip that. Again, 3 zeros are there in the second row, need to skip that again. Similarly, we can see that even after scanning all the rows, we do not get any of the zeros assigned. So we switch on to the column scan. Here, there is a single zero in the third column. So assign that and cross the zeros in the corresponding row. Again, in the fourth column, assign this 0. Since we are unable to assign all these zeros, we repeat the same scanning process. As you can see, this will not be possible. So when this situation arises, we have two possibilities and two cases arise here. Case 1, we assign this 0, that is in the third row in the first column, and then after row scanning, we assign the remaining zeros as well. Now we can see that the number of assigned zeros is equal to the order of the matrix, that is 4. But just in case, if assigned zeros are not equal to the order of the matrix, we have to opt for the tick marking method, and that is also being explained in the last video. After the assignment, we need to check whether all the cities are traversed or not. So we can see that from city A, we move to city D, from city D to B, from B to C, and from C back to A. Thus, in this case, each city is traversed only once except the origin city A, As there are no loops or subloops in our case, this means the optimal route is obtained. That is A, D, B, C, A. Thus, the cost associated with the route is 28,000 rupees, and the goods will be delivered from Surat to Indore, Indore to Mumbai, Mumbai to Jaipur, and from Jaipur back to Surat. Now, considering the case 2, here we assign the 0 in the third row and second column, and thus we assign the remaining zeros. The number of assigned zeros is equal to the order of the matrix. Now, checking for any subloops. Here you can see that there is a subloop, that is when a person travels from city A to D, he returns back to the same city A without traversing the cities B and C. This does not give us the optimal path. So, for such cases, we choose the next minimum element after 0 in our final matrix, that is 1 in our case. This way the whole process of assigning repeats. You can try this yourself. In fact, you can pause the video here and check it yourself that again 2 cases will be formed. We have already obtained the optimal route for this specific case because you can see that we got the optimal path in the case 1 itself. So taking any minimum element other than 0, the cost will definitely increase by that factor.
I hope you must have got the gist of how this can be solved.
Yes, absolutely.
Great then. See you soon. I have to catch a train.
Yeah, sure.
Bye. Happy journey.
Thanks for watching this video. If you found this content informative, hit that subscribe button. And if you have any suggestions or queries, don't forget to write in the comment section below. If you don't want to miss any of our videos, click on the bell icon to get notified every time we come up with something new. Thank you.